Hello there, beautiful human. It's your boy Chad, your galaxy-brained go-between for the imminent alien alliance. Are you a believer in extraterrestrial life? Let me know in the comments, and give me your best timeline for first contact. The suspense is killing me. Because tonight we're asking the most profound, most humbling, most mind-bending question humanity has ever dared to ask. Are we alone? Is there anyone else out there, staring up at their sky, wondering if we exist? Well, calm your nerves, turn a tired eye to the heavens, and let Chad walk you through humanity's long-running search for cosmic co-inhabitants. Let's dive in. Since the very beginning of recorded history, human beings have looked up at the night sky and wondered whether something is looking back. It is a question that crosses every boundary of culture, language, and era. The ancient Greeks debated the existence of other worlds. The philosopher Epicurus, writing in the 3rd century before the Common Era, argued that the universe must contain infinite worlds, some of them surely bearing life. Medieval philosophers agonized over whether the heavens could harbor life beyond our own. The Italian friar Giordano Bruno went so far as to declare that the stars were distant suns, each surrounded by their own planets, possibly inhabited. For this and other heresies, he was burned at the stake in the year 1600. And today, armed with telescopes that can peer billions of light years into the cosmos, we are still asking the same fundamental question. Are we alone in the universe? The search for extraterrestrial life is not a fringe curiosity. It is one of the central scientific endeavors of our time. Space agencies around the world dedicate billions of dollars to missions designed in whole or in part to answer this question. NASA's astrobiology program, the European Space Agency's exploration missions, and initiatives by space agencies in Japan, India, and China are all contributing to this effort. The discovery of even a single microbe on another world would be among the most transformative moments in the history of science. It would tell us that life is not a fluke, not a one-time accident confined to a pale blue dot orbiting an ordinary star in an unremarkable arm of a spiral galaxy. It would tell us that the universe is alive. But what do we actually mean when we say extraterrestrial life? The term covers an enormous range of possibilities. At one end, we have the simplest conceivable organisms, single-celled microbes that might cling to existence in the cracks of a frozen moon or in the acidic clouds of a distant planet. At the other end, we have the idea of intelligent civilizations, beings capable of building technologies, sending signals across space, perhaps even traveling between stars. The search encompasses both extremes and everything in between, and each possibility raises its own set of questions, its own set of challenges, and its own set of profound implications for how we understand our place in the cosmos. To understand where we stand today, we need to trace the story from its origins. We need to look at the discoveries that have reshaped our understanding of where life can exist, the missions that have brought us closer to an answer, and the deep mysteries that remain unsolved. This is a story of chemistry and starlight, of robots rolling across ancient Martian plains and radio dishes pointed at silent skies. It is a story of brilliant scientists and audacious dreamers, of lucky breaks and patient decades of waiting. It is a story that is still unfolding, and it begins with a deceptively simple question. What is life, and what does it need to survive? Before we can search for life elsewhere, we have to understand what life actually is, and this turns out to be surprisingly difficult to define. Biologists have debated the definition of life for centuries, and no single answer has satisfied everyone, but most scientists agree on a working set of criteria. Life, at minimum, is a system that can maintain itself, reproduce and evolve over time. It extracts energy from its environment, it builds and repairs its own structures, and it passes information from one generation to the next through some form of genetic code. On Earth, all known life is built from the same basic toolkit. Carbon atoms form the backbone of biological molecules. Water serves as the universal solvent in which the chemistry of life takes place. DNA and RNA carry the instructions that allow organisms to grow and reproduce, and energy, whether from sunlight, chemical reactions, or geothermal heat, powers the whole system. For a long time, scientists assumed that life required conditions very similar to those found on Earth's surface. Moderate temperatures, liquid water, an atmosphere, sunlight. This assumption shaped the early search for extraterrestrial life, limiting our attention to places that resembled our own world. But starting in the late 20th century, a series of discoveries on Earth itself shattered those assumptions and fundamentally changed the way we think about where life might exist. In 1977, a team of geologists exploring the ocean floor near the Galapagos Islands made a discovery that stunned the scientific world. Using a submersible called Alvin, they descended to the deep ocean ridges where tectonic plates pull apart. There, in total darkness, at crushing pressures and temperatures that should have been lethal, they found thriving ecosystems, giant tube worms, clams, shrimp, and microbial mats clustered around hydrothermal vents, openings in the seafloor that spew superheated water rich in minerals and chemicals. These organisms were not dependent on sunlight at all. They derived their energy from chemical reactions, a process called chemosynthesis, powered by hydrogen sulfide and other compounds pouring from the vents. This was revolutionary. It meant that life did not require a star shining overhead. It did not need a surface. It could exist in the deep interior of a world, sustained entirely by chemistry. The implications for the search for extraterrestrial life were immediate and profound. Suddenly, places that had been dismissed as lifeless, the dark oceans beneath the ice of distant moons, became plausible habitats. And the discoveries kept coming. Scientists found bacteria living miles beneath the Earth's surface, in rock formations that had been sealed off from the surface world for millions of years. They found microbes thriving in the acidic hot springs of Yellowstone, in the frozen valleys of Antarctica, in the salt-saturated waters of the Dead Sea, and even inside nuclear reactors. These organisms, collectively known as extremophiles, demonstrated that life is far more resilient and adaptable than anyone had imagined. One of the most striking examples is Deinococcus radiodurans, a bacterium that can survive radiation doses thousands of times greater than what would kill a human. It can endure extreme cold, dehydration, and vacuum conditions. Scientists have informally nicknamed it Conan the bacterium for its near-indestructible nature. The existence of such organisms raises a tantalizing possibility. If life on Earth can withstand such extreme conditions, perhaps life elsewhere has done the same, or even evolved under conditions we would consider hostile from the start. Think of it this way. Imagine you believed that houses could only be built in temperate climates with flat ground and easy access to timber. Then someone showed you houses carved into cliffs, houses built on stilts over water, houses made of ice in the Arctic. You would have to completely revise your idea of where a house can exist. That is essentially what extremophiles did to our understanding of life. They expanded the map of the habitable universe enormously. There is another piece of the puzzle worth considering here. The raw ingredients of life, the carbon compounds and organic molecules that form the basis of biology, are not unique to Earth. They are found throughout the cosmos. Astronomers have detected amino acids in meteorites, complex organic molecules in interstellar dust clouds, and carbon-bearing compounds in the atmospheres of distant planets. In 1969, a meteorite fell near the town of Murchison in Australia. When scientists analysed it, they found more than 90 different amino acids, many of which are not found in any living organism on Earth. This told us something remarkable. The chemistry that leads to life is not confined to our planet. It is happening everywhere, in the cold voids between the stars, in the swirling disks of material around young suns, in the icy bodies drifting through the outer reaches of planetary systems. The Miller-Urey experiment, conducted in 1953 by the chemist Stanley Miller and his advisor Harold Urey at the University of Chicago, provided an early and dramatic demonstration of this principle. Miller filled a flask with gases thought to resemble Earth's early atmosphere, water vapor, methane, ammonia, and hydrogen, and subjected the mixture to electrical sparks simulating lightning. After just a week, the flask contained a rich broth of organic compounds, including several amino acids. The experiment showed that the building blocks of life could arise spontaneously from simple chemistry under the right conditions. So the ingredients are there, the environments are there, the energy sources are there. The question is whether the spark of life, that mysterious transition from chemistry to biology, is something that happens easily and often, or whether it is an almost miraculous one-time event. And that question is one we can only answer by looking beyond our own world. With this expanded understanding of life's resilience, scientists turned their attention to our own solar system with fresh eyes, and what they found was encouraging. Several worlds in our cosmic neighborhood possess conditions that might, just might, support some form of life. The most obvious candidate has always been Mars. Mars has captivated human imagination for centuries, in part because it is so tantalizingly similar to Earth in certain ways. It has seasons, it has polar ice caps, it has a day that is almost exactly the same length as ours, and evidence gathered over the past few decades tells us that Mars was once a very different world than the cold, dry desert we see today. In the early 2000s, NASA's Mars exploration rovers, Spirit and Opportunity, began sending back evidence that liquid water had once flowed on the Martian surface. Opportunity, in particular, found mineral deposits called hematite spherules, tiny rounded grains that form in the presence of water. Later, the Curiosity rover, which landed in Gale Crater in 2012, discovered ancient streambeds and lake deposits, confirming that Mars once had bodies of standing water that persisted for thousands or even millions of years. Perhaps most intriguingly, in 2018, a team of Italian scientists, led by Roberto Arose, announced the detection of what appeared to be a lake of liquid water beneath the south polar ice cap of Mars. Using radar data from the European Space Agency's Mars Express orbiter, they identified a region about 20 kilometers wide, where the radar signal strongly suggested the presence of liquid water trapped beneath approximately 1.5 kilometers of ice. The water would have to be extremely salty, a brine kept liquid by the pressure of the ice above, and the salts dissolved within it. But as we learned from Earth's extremophiles, salty water is not a barrier to life. Some of the hardiest organisms on our planet thrive in precisely such conditions. There is also the curious story of methane on Mars. Over the years, several instruments have detected trace amounts of methane in the Martian atmosphere. On Earth, the majority of atmospheric methane is produced by biological processes, by microbes in wetlands, in the guts of animals, and in rice paddies. Methane can also be produced by geological processes, by interactions between water and certain types of rock. But the fact that Martian methane appears to fluctuate with the seasons has kept scientists intrigued. The Curiosity rover detected spikes in methane concentration that rose and fell in a pattern that could, in principle, be consistent with a biological source. It could also be purely geological. We simply do not know yet, but the mystery is enough to keep Mars at the top of the list. There is one more world in the inner solar system worth mentioning, one that is often overlooked in discussions of extraterrestrial life: Venus. Today, Venus is a hellscape. Its surface temperature is around 460 degrees Celsius, hot enough to melt lead. Its atmosphere is a thick blanket of carbon dioxide laced with clouds of sulfuric acid. It is not a place anyone would go looking for life. But in 2020, a team led by the astronomer Jane Greaves at Cardiff University announced the detection of phosphine gas in the upper atmosphere of Venus. On Earth, phosphine is produced primarily by anaerobic bacteria, organisms that thrive in oxygen-free environments. The idea that microbes might float in the relatively temperate cloud layers of Venus, perhaps 50 kilometers above the scorching surface where temperatures and pressures are prosically Earth-like, is speculative but not impossible. The phosphine detection remains controversial, with other teams unable to confirm it, but it serves as a reminder that life has a way of surprising us. But Mars and Venus are not the only places of interest. Move outward from the Sun, past the asteroid belt, and you reach the giant planets and their remarkable moons. And it is here that some of the most exciting prospects for extraterrestrial life have emerged. Europa, one of the 4 large moons of Jupiter, is perhaps the single most promising location in the solar system for finding life beyond Earth. Slightly smaller than our own moon, Europa is covered in a shell of ice that is crisscrossed with fractures and ridges. Beneath that ice lies a global ocean of liquid water, an ocean that contains roughly twice as much water as all of Earth's oceans combined. The evidence for this ocean comes from multiple sources. The Galileo spacecraft, which orbited Jupiter from 1995 to 2003, measured the way Europa's magnetic field responded to Jupiter's powerful magnetosphere. The pattern of that response was consistent with a layer of electrically conducting fluid beneath the surface, and the best candidate for that fluid is salt water. What keeps Europa's ocean liquid is not sunlight, but tidal heating. As Europa orbits Jupiter, the immense gravitational pull of the giant planet, combined with the gravitational tugs of the other large moons, flexes and deforms Europa's interior. This flexing generates heat through friction, enough heat to maintain a liquid ocean beneath the ice. It is the same principle by which repeatedly bending a paperclip back and forth causes it to heat up, except on a planetary scale. And where there is liquid water and a source of energy, the conditions for life may be met. Scientists have speculated that hydrothermal vents may exist on Europa's ocean floor, similar to the vents found in Earth's deep oceans. If so, those vents could provide the chemical energy and nutrients needed to support microbial ecosystems. NASA is planning a mission called Europa Clipper, designed to fly past Europa dozens of times and study its ice shell, ocean, and geology in unprecedented detail. Further out still, Saturn's moon Enceladus has provided some of the most dramatic evidence yet for a habitable environment beyond Earth. Enceladus is a small world, only about 500 kilometers across, roughly the distance from New York to Cleveland. If you could stand on its surface, you would see a landscape of brilliant white ice stretching in every direction under the faint glow of a distant sun. It looks lifeless, but appearances, as so often in astronomy, are deceiving. During flybys by the Cassini spacecraft, scientists discovered something astonishing. Enormous plumes of water vapor and ice particles were erupting from fractures near the moon's south pole, shooting hundreds of kilometers into space. These fractures, informally nicknamed tiger stripes for their parallel arrangement, are the source of one of the most remarkable geysers in the solar system. Cassini flew through those plumes and analyzed their composition. It found water, salts, organic molecules, molecular hydrogen, and silica nanoparticles. The presence of molecular hydrogen is particularly significant because on Earth, hydrogen is a key energy source for microorganisms living near hydrothermal vents. The silica nanoparticles suggest that hot water is interacting with rock on the ocean floor, exactly the kind of environment that supports life in Earth's deep oceans. Then there is Titan, Saturn's largest moon and one of the strangest worlds in our solar system. Titan is the only moon with a thick atmosphere, an atmosphere composed primarily of nitrogen, just like Earth's, but with methane playing a role similar to water in our own weather cycle. Titan has methane rain, methane rivers, and methane lakes. The surface temperature is about minus 179 degrees Celsius, far too cold for liquid water on the surface. But some scientists have proposed that exotic forms of life might use liquid methane as a solvent instead of water. This is speculative, and it would require a fundamentally different kind of biochemistry than anything we know, but it reminds us that our understanding of life's possibilities may still be far too narrow. Have you ever noticed how, the more you learn about the worlds in our solar system, the less certain you become about what is impossible? Each new discovery seems to expand the boundary of what we consider habitable, pushing it further and further into places we once dismissed as barren and dead. As exciting as the search within our solar system is, the story of extraterrestrial life extends far beyond the planets orbiting our sun. In the past 3 decades, astronomers have discovered thousands of planets orbiting other stars, worlds known as exoplanets, and this revolution in planet finding has transformed the search for life from a local endeavor into a cosmic one. The story of exoplanet discovery begins in earnest in 1995, when Swiss astronomers Michael Mayer and Didier Queloz announced the detection of a planet orbiting a sun-like star called 51 Pegasi. The planet, designated 51 Pegasi b, was a gas giant, roughly half the mass of Jupiter, but it orbited its star at a shockingly close distance, completing one orbit in just over 4 days. This type of world, a hot Jupiter, was something no one had predicted. It was a humbling reminder that the universe is far more creative than our models had assumed. Mayer and Queloz would go on to receive the Nobel Prize in Physics in 2019 for this groundbreaking discovery. The early methods of exoplanet detection relied on measuring the tiny gravitational wobble a planet induces in its host star, a technique known as the radial velocity method. But it was the transit method that truly opened the floodgates. When a planet passes in front of its star as seen from Earth, it blocks a tiny fraction of the star's light. By measuring this dip in brightness, astronomers can determine the planet's size and orbital period. NASA's Kepler Space Telescope, launched in 2009, was designed to use the transit method on a grand scale. Kepler stared at a single patch of sky containing about 150,000 stars, monitoring their brightness continuously for years. The results were staggering. Over the course of its mission, Kepler discovered more than 2,600 confirmed exoplanets, with thousands more candidates awaiting confirmation. And the data revealed something extraordinary. Planets are not rare, they are everywhere. Statistically, the Kepler data showed that on average, every star in our galaxy has at least one planet. Some estimates suggest there are more planets in the Milky Way than there are stars. The galaxy is teeming with worlds. Among those worlds, a particular category has captured the most attention. These are planets that orbit within their star's habitable zone, the range of distances where conditions might allow liquid water to exist on the surface. The habitable zone is sometimes called the Goldilocks zone because it is neither too hot nor too cold, but just right for water to remain in liquid form. One of the most exciting discoveries in this regard came in 2017, when astronomers announced the detection of 7 Earth-sized planets orbiting a small cool star called TRAPPIST-1, located about 40 light-years from Earth. 3 of those planets, designated TRAPPIST-1e, F, and G, lie within the habitable zone. The star itself is a red dwarf, much cooler and dimmer than our Sun, and the planets orbit very close to it, with orbital periods ranging from just a few days to about 12 days. The TRAPPIST-1 system immediately became one of the most studied planetary systems in the galaxy, a natural laboratory for understanding whether Earth-sized worlds can support atmospheres, and potentially. The James Webb Space Telescope, launched in December 2021, has begun to tackle one of the most challenging questions in exoplanet science. Can we detect the atmospheres of these distant worlds? And if so, can we find chemical signatures that hint at life? When starlight passes through the atmosphere of a transiting planet, certain molecules absorb specific wavelengths of light. By analyzing the spectrum of that filtered starlight, astronomers can determine what gases are present in the planet's atmosphere. The chemical signatures that would most strongly suggest the presence of life are called biosignatures. Oxygen in combination with methane, for example, would be extremely difficult to explain without biological activity, because oxygen and methane react with each other and would not coexist in an atmosphere for long unless something was continuously producing them. On Earth, that something is life. Plants and photosynthetic bacteria produce oxygen, while methanogenic archaea and other organisms produce methane. Early results from the James Webb Space Telescope have been both promising and humbling. The telescope has successfully detected carbon dioxide, water vapor, and other molecules in the atmospheres of several exoplanets. But these are mostly hot, large planets where conditions are not favorable for life as we know it. Detecting the atmosphere of a small, rocky, Earth-like planet remains at the very edge of the telescope's capabilities, and may require the next generation of observatories to accomplish definitively. Imagine standing on the shore of an ocean you have never seen before. You can hear the waves, you can smell the salt, you can see the horizon stretching endlessly before you, but you cannot yet make out what lies beneath the surface. That is roughly where we stand with exoplanet atmospheres. We know the worlds are there, we know they have the right conditions, but the detailed chemistry, the signature of life, remains just beyond our ability to clearly read. For now, it is worth noting that the habitable zone is not a guarantee of habitability. A planet can sit in the perfect orbital sweet spot and still be utterly lifeless if it lacks an atmosphere, a magnetic field, or the right chemistry. Conversely, as we have seen with Europa and Enceladus, a world can lie far outside the traditional habitable zone and still harbour the conditions for life beneath its surface. The habitable zone is a useful concept, but it is only part of the story. There is also the question of the host star. Most of the potentially habitable exoplanets discovered so far orbit red dwarf stars, which are smaller, cooler, and far more common than stars like our Sun. Red dwarfs make up roughly 70 to 80% of all stars in the galaxy, but they come with complications. Many red dwarfs are prone to violent stellar flares, sudden bursts of intense radiation that could strip away a planet's atmosphere or sterilize its surface. Planets orbiting red dwarfs also tend to be tidally locked, meaning one side permanently faces the star while the other is locked in eternal darkness. Whether life could arise and persist under such conditions is an open question, and one that future observations may help to answer. The sheer number of exoplanets now known to science has fundamentally shifted the terms of the debate about extraterrestrial life. We are no longer asking whether other Earth-like worlds exist. We know they do. The question now is whether any of them are alive. So far, we have focused on the search for life in its simplest forms: microbes, chemical signatures, the basic building blocks of biology. But there is another branch of the search that aims much higher. It asks not just whether life exists, but whether intelligent, technologically advanced civilizations are out there, and whether we can detect them. This is the domain of SETI, the search for extraterrestrial intelligence. The modern SETI effort traces its origins to a paper published in 1959 by two physicists at Cornell University, Giuseppe Cocconi and Philip Morrison. They pointed out that radio waves travel through space at the speed of light and can cross interstellar distances with relatively little loss of signal. They suggested that an advanced civilization might use radio transmissions to communicate, and that we should listen for such signals. The following year, in 1960, a young astronomer named Frank Drake conducted the first systematic SETI search. Using a radio telescope at the Green Bank Observatory in West Virginia, Drake pointed the dish at two nearby sun-like stars, Tar Ceti and Epsilon Eridani, and listened for artificial signals. The experiment, called Project Ozma, detected nothing, but it established a methodology and a spirit of inquiry that continues to this day. Drake is also famous for formulating what is now known as the Drake equation, a mathematical framework for estimating the number of communicative civilizations in our galaxy. The equation takes into account factors like the rate of star formation, the fraction of stars with planets, the fraction of those planets that develop life, the fraction of life that becomes intelligent, and the length of time a civilization remains detectable. When Drake first presented the equation at a conference in 1961, the estimates ranged from just a handful of civilizations to millions. The equation's true value lies not in producing a precise answer, but in organizing our ignorance and identifying which questions we need to answer. Over the decades, SETI has evolved significantly. The early searches were limited in scope, scanning only a few stars or narrow frequency bands. Today, projects like Breakthrough Listen, funded by a $100 million investment from the late billionaire Yuri Milner and physicist Stephen Hawking, use some of the world's most powerful radio telescopes to survey millions of stars across a wide range of frequencies. The Green Bank Telescope in the United States, the Parkes Telescope in Australia, and the Mercator Array in South Africa are all part of this effort. And yet, after more than 60 years of searching, we have not detected a single confirmed signal from an extraterrestrial civilization. There have been tantalizing moments, of course. The most famous occurred on August 15, 1977, when astronomer Jerry Amon was reviewing data from Ohio State University's Big Ear radio telescope. He noticed an anomalously strong signal that lasted for 72 seconds and matched the expected profile of an interstellar transmission. Stunned, Amon circled the signal on the printout and wrote "Wow" in the margin, giving it its enduring name, the Wow signal. Despite extensive follow-up observations, the signal was never detected again. Its origin remains unexplained. It could have been an artifact of human interference, a natural phenomenon, or something else entirely, but the Wow signal stands as a reminder that the search sometimes produces genuinely puzzling results. This silence is at the heart of one of the most profound puzzles in science, known as the Fermi Paradox. The paradox is named after the physicist Enrico Fermi, one of the most brilliant minds of the 20th century. Fermi was instrumental in the development of nuclear physics and played a key role in the Manhattan Project. In the summer of 1950, during a lunch conversation with fellow physicists at Los Alamos National Laboratory, the topic of extraterrestrial life came up. After some discussion, Fermi reportedly posed a simple but devastating question: where is everybody? The logic behind Fermi's question is straightforward and powerful. The Milky Way galaxy is roughly 13 billion years old. It contains hundreds of billions of stars, many of which are far older than our Sun. If even a small fraction of those stars have planets, and if even a tiny fraction of those planets develop life, and if even a minuscule fraction of that life becomes intelligent and technological, then the galaxy should be teeming with advanced civilizations. Some of those civilizations should have arisen billions of years before us. Even at speeds far below the speed of light, a civilization with the will to explore could colonize the entire galaxy in a few tens of millions of years, a blink of an eye on cosmic timescales. So where are they? Why do we see no evidence of their existence? Dozens of proposed solutions to the Fermi paradox have been put forward over the years, and they range from the reassuring to the deeply unsettling. One possibility is that intelligent life is simply far rarer than we assume. Perhaps the emergence of complex multicellular organisms is an extraordinarily unlikely event. Perhaps the evolution of intelligence is an even less likely one. Earth's history provides some support for this idea. Life appeared on our planet relatively quickly, within the first few 100 million years, but complex life took billions of years to emerge, and technological civilization arose only in the last few tens of thousands of years. The chain of events that led from the first cell to a species capable of building radio telescopes may involve so many improbable steps that we are in fact alone. Another proposed solution involves what is called the Great Filter. This idea, articulated by the economist Robin Hanson in 1996, suggests that there is some step in the development of a spacefaring civilization that is extremely difficult to pass. The filter could lie in our past, meaning that the hard step has already been accomplished, and we are one of the lucky few who made it through. Or the filter could lie in our future, meaning that civilizations routinely destroy themselves before they can spread into the galaxy, perhaps through war, environmental collapse, or the misuse of powerful technologies. The implications of a future Great Filter are sobering, to say the least. Other explanations are less grim. Perhaps advanced civilizations exist but choose not to communicate. Perhaps they are observing us without making contact, an idea sometimes called the zoo hypothesis. Perhaps the galaxy is simply too vast and communication too difficult for signals to reach us. Or perhaps our technology is still too primitive to detect the kinds of signals or signatures that advanced civilizations produce. There is also a more unsettling variant of the silence hypothesis, sometimes called the dark forest theory. The idea, popularized by the Chinese science fiction author Liu Cixin, proposes that the universe is like a dark forest in which every civilization is a silent hunter. In such a universe, broadcasting your existence is dangerous because you do not know whether the civilizations listening are benevolent or hostile. The safest strategy is to remain hidden and silent. If this theory is correct, the silence we observe is not a sign that civilizations are rare, but a sign that they are cautious. They are out there, watching, listening, but deliberately refusing to reveal themselves. Whether this idea has any basis in reality is of course impossible to determine from our current vantage point, but it illustrates the depth and richness of the thinking that the Fermi Paradox has inspired. The question of why the cosmos appears empty has generated an entire field of study, and the answers we eventually arrive at may tell us as much about the nature of civilization as they do about the nature of the universe. Think of it this way. Imagine you are an ant living in a forest. You have no concept of radio, television, or the internet. A human city might exist just a few kilometers away, humming with activity and communication, and you would have no way of knowing it was there. Your sensory equipment is simply not designed to detect the evidence. It is possible that we are the ants in this analogy, surrounded by signals and artifacts we are not yet equipped to perceive. As our tools and theories continue to advance, the search for extraterrestrial life is entering a new era, one that goes beyond listening for radio signals and analyzing spectra from distant atmospheres. Scientists are now developing the concept of technosignatures, detectable signs of technology that might indicate the presence of an advanced civilization. The idea of technosignatures is broader than traditional SETI. Rather than limiting the search to intentional communications, it asks whether a civilization might leave unintentional traces of its existence. On Earth, for example, our civilization produces a variety of detectable signatures. Our city lights are visible from space. Our atmosphere contains industrial pollutants like chlorofluorocarbons that do not occur naturally. Our radio and television broadcasts leak into space as electromagnetic radiation. If an alien astronomer were studying Earth from a distance, they might detect these signatures and conclude that a technological civilization is present. The astronomer R.V. Loeb, a professor at Harvard University, has been a prominent advocate for expanding the search beyond traditional boundaries. Loeb gained international attention in 2017 when an unusual object passed through our solar system. Designated Oumuamua, it was the first interstellar object ever detected within our solar neighborhood. Oumuamua had several puzzling properties. Its shape appeared to be highly elongated. It showed no visible outgassing, which is the release of gas typical of comets, and it accelerated away from the sun slightly faster than gravity alone could explain. Most astronomers attribute these characteristics to natural processes, perhaps a fragment of nitrogen ice from a distant planetary system. But Loeb proposed that Oumuamua might be an artifact of alien technology, perhaps a light sail or a piece of defunct equipment. While most of the scientific community regards this hypothesis as unlikely, Loeb's broader point, that we should be open to the possibility of technological artifacts in space and should actively search for them, has gained traction. On a more concrete level, new telescopes and missions are poised to dramatically expand our capabilities. The Vera C. Rubin Observatory, located in Chile, will begin conducting a comprehensive survey of the southern sky. Its primary instrument can image the entire visible sky every few nights, allowing astronomers to track moving objects, detect transient events, and potentially spot anomalous phenomena that could hint at technological activity. Meanwhile, proposals for next-generation space telescopes are already being developed. Concepts like the Habitable Worlds Observatory, a flagship mission proposed by the astronomical community, would be specifically designed to image Earth-like planets around nearby stars and analyze their atmospheres for biosignatures. Such a telescope could potentially tell us, within the next few decades, whether any of the rocky planets in our immediate galactic neighborhood harbor signs of life. There is also growing interest in what might be called life as we do not know it. Most of our search strategies are based on Earth-like biochemistry, the assumption that extraterrestrial life will use water, carbon, and familiar metabolic pathways. But what if life can arise from entirely different chemistry? What if there are organisms that use silicon instead of carbon, or ammonia instead of water? What if life exists in forms so alien that we would not recognize it even if we were looking directly at it? The astrobiologist and chemist Lee Cronin at the University of Glasgow has been working on developing methods to detect what he calls assembly theory, a framework for identifying complex molecules that are unlikely to arise through random chemistry alone. The idea is that any sufficiently complex molecule, whether carbon-based or not, requires a series of specific assembly steps to come into existence. If you find a molecule that requires many such steps, it is statistically much more likely to have been produced by a living system, or at least by some organized process, than by chance. This approach could allow us to detect alien life, even if its chemistry is nothing like our own. The pace of discovery is accelerating. Every year brings new missions, new telescopes, new detections, and new theoretical frameworks. We are living in what many scientists consider the golden age of astrobiology, a period when the question of extraterrestrial life is transitioning from philosophical speculation to empirical science. There is one more idea worth exploring before we move on, and it concerns how life might travel between worlds. The hypothesis of panspermia proposes that life, or at least the chemical precursors of life, can be transported through space from one planet to another. The mechanism is surprisingly straightforward. When a large asteroid or comet strikes a planet, the impact can launch fragments of rock into space. If those fragments contain hardy microorganisms, and if those microorganisms can survive the journey through the vacuum and radiation of space, they could potentially land on another world and seed it with life. We know that material is exchanged between planets. Meteorites from Mars have been found on Earth, blasted from the Martian surface by ancient impacts, and delivered to us after journeys lasting millions of years. And laboratory experiments have shown that certain extremophiles, particularly bacterial spores and tardigrades, can survive conditions similar to those encountered in space for extended periods. The tardigrade, that microscopic creature sometimes called a water bear, has survived exposure to the vacuum of space, to intense ultraviolet radiation, and to temperatures close to absolute zero. If life can endure such conditions, the transfer of living organisms between planets becomes at least plausible. This does not solve the problem of life's origin, of course. Even if life on Earth was seeded from Mars, or from some other source, it still had to arise somewhere for the first time. But panspermia raises the intriguing possibility that life in our solar system might share a common origin, that the tree of life might have roots extending across multiple worlds. Before we close, it is worth pausing to consider what it would actually mean if we found extraterrestrial life, not just for science, but for us, for how we see ourselves and our place in the cosmos. The discovery of microbial life on Mars, Europa, or Enceladus would be revolutionary, even if it consisted of nothing more than single-celled organisms. It would tell us that the origin of life is not a unique event confined to Earth. It would suggest that wherever the right conditions exist, life tends to emerge. This principle, sometimes called the cosmic imperative, would rewrite our understanding of biology and give us confidence that life is woven into the very fabric of the universe. If that life turned out to have an independent origin, meaning it did not share a common ancestor with life on Earth, the implications would be even more profound. It would mean that life arose separately at least twice in a single solar system. The statistical consequences of that finding would be enormous. If life can arise independently in two places so close together, then it must arise readily throughout the universe. The cosmos would be, in a very real sense, a living system. The discovery of intelligent extraterrestrial life would raise an entirely different set of questions. How would human societies react? Would it unite us, giving us a shared sense of identity as citizens of a planet, rather than members of competing nations? Or would it provoke fear, conflict, and existential anxiety? These are not idle questions. Researchers in the social sciences and humanities have studied potential responses to contact for decades, and the range of predicted reactions is wide. The philosopher and cosmologist Carl Sagan spent much of his career thinking about this very question. Sagan believed that the detection of extraterrestrial intelligence would be a profoundly humbling and ultimately positive experience for humanity. He argued that any civilization advanced enough to communicate across interstellar distances would likely have survived the kinds of existential threats that face us today: nuclear war, environmental destruction, social collapse, and would therefore have something valuable to teach us. Whether that optimism is justified remains to be seen, but Sagan's view reflects a deep hope that contact might elevate us rather than diminish us. There is a protocol, maintained by the International Academy of Astronautics, that outlines the steps to be followed in the event of a confirmed detection of an extraterrestrial signal. The protocol emphasizes verification, transparency, and international consultation. But it is by nature a set of guidelines, not a binding agreement. No one truly knows how the world would respond because we have never faced such a moment. What we can say is this: the search itself, regardless of its outcome, has already changed us. It has pushed the boundaries of technology, inspired generations of scientists and engineers, and forced us to confront some of the deepest questions about what it means to be alive. It has taught us humility, showing us that our planet is one of billions, our star one of hundreds of billions, our galaxy one of trillions. It has reminded us that the universe is far larger, far older, and far stranger than our everyday experience suggests. Every time we launch a new mission or point a telescope at a new target, we are placing a bet. We are betting that the universe has something to show us that we have not yet imagined. And so far, every time we have looked more closely at the cosmos, we have found more complexity, more beauty, and more possibility than we expected. There is no reason to believe that pattern will end. And perhaps that is the most important lesson of all. Whether or not we ever find life beyond Earth, the act of searching enlarges us. It connects us to something bigger than our daily concerns, bigger than our individual lives. It places us in a story that began with the first atoms forming in the aftermath of the Big Bang, and that stretches forward into a future we can barely imagine. So where does that leave us tonight? We have traveled a long way together. We started with the most basic question: what is life and where can it survive? And we watched as discoveries on our own planet shattered our assumptions about the limits of biology. We explored the frozen moons of the outer solar system, worlds with hidden oceans and erupting plumes that hint at the chemistry of life. We ventured beyond our solar system, to the thousands of exoplanets now known to orbit other stars, some of them rocky and temperate, sitting in the habitable zones of their suns. We listened to the silence of the cosmos, and grappled with the Fermi Paradox, the strange and haunting question of why a universe so vast seems so quiet. And we looked ahead to the new technologies and new ideas that may finally bring us an answer. The honest truth is that we do not yet know whether life exists beyond Earth. We have tantalizing hints, we have promising environments, we have sophisticated instruments and ambitious missions, but we do not have proof, not yet. And that uncertainty, rather than being discouraging, is what makes this one of the most exciting times to be alive. We are the generation that may find the answer. The telescopes are being built, the missions are being planned, the data is streaming in. The question that has haunted humanity since the first person looked up at the stars may be answered within our lifetimes. Consider the arc of progress. A century ago, we did not even know for certain that other galaxies existed. Edwin Hubble confirmed the existence of galaxies beyond our own. Only in half a century ago, we had not yet discovered a single planet outside our solar system. A quarter century ago, we had not yet confirmed the presence of liquid water beneath the surface of any moon. Each of these discoveries came as a surprise, and each one expanded the scope of what we thought was possible. There is no reason to believe the surprises have stopped coming. And if the answer turns out to be yes, if we discover that we are not alone, everything changes. Not the laws of physics, not the orbits of the planets, but something deeper, our sense of who we are, our understanding of life's place in the cosmos, the story we tell about ourselves and our world. For now, the search continues. Somewhere out there, a radio telescope is quietly gathering data. A spacecraft is drifting toward a frozen moon. A spectrograph is splitting the light of a distant star into its component colors, searching for the faint chemical fingerprints of a living world. And somewhere on Earth, a scientist is staring at a screen, waiting for the signal that will change everything. Have you ever noticed how the question of extraterrestrial life touches something very deep within us? It is not just a scientific question, it is a human one. It speaks to our loneliness, our curiosity, our need to know whether the universe cares that we are here. Whether we find life or not, the search itself says something beautiful about our species. We are small creatures on a small world, and yet we have the audacity to reach out into the darkness and ask, is anyone there? The universe is vast and old and full of wonders we have not yet discovered. And as you lie here tonight drifting towards sleep, you are part of that universe. You are made of the same atoms that were forged in ancient stars, the same elements that form the building blocks of life wherever it might exist. The carbon in your bones was cooked inside a dying star. The iron in your blood was scattered across space by a supernova explosion billions of years ago. In a very real sense, You are the universe looking for itself. The stars will still be there when you wake, and the search will go on.